Okay. Yeah, hello. I want to present a project to you which I've been working on the past couple of months, which is called Badkeys. So a quick introduction about me. If you're from Germany, you might know me from writing for golem.de, which is kind of one of the big German IT news websites. I'm also writing a monthly newsletter about TLS, and I have discovered a couple of TLS vulnerabilities in the past. And a quick mentioning of my sponsor here. Like, I'm doing this in collaboration with IT University of Copenhagen, and they have a project called CITY, which stands for Cyber Secure IoT in Danish Industry, and they are funding so that I can do this work. So yeah, thanks for that. A few months ago, there was a news. This was a blog post from GitHub where they said, okay, they are revoking some SSH keys. They had been generated by a software called Gitkraken, which is apparently some Git client that people tend to use and generate their SSH keys with, and that was using a JavaScript library called keypair, which resulted in cryptographic keys that could be broken because they had some bugs in their random number generation. And there was a discussion on lobsters. I don't know if you know lobsters. It's like Hacker News, but smaller. And their user asked, there's no have I been pawned for public keys as far as I know. I thought, there isn't, but maybe I should create one, and now there is. And that is Badkeys. It's basically a web page and a tool and a library to check cryptographic keys for known vulnerabilities. I guess most of you know public key cryptography. We have this thing where we have a private key and a public key, and sometimes things go wrong, and then there are private keys that are not private because either they can be found on the internet or because they can be broken because something was wrong in the key generation. So there were many vulnerabilities in this class. Like, there was the Debian OpenSSL bug, the older people will remember. Then there's a problem with common prime factors. There was the ROCA attack, which caused Estonia, they had to replace thousands of their ID cards. And then there was this keypair bug last year. Then I discovered a kind of new attack, or a kind of old new attack, because it's been known since hundreds of years, like long before cryptography even was a thing, but I kind of discovered that this is the real attack you can apply to real devices in the wild. And then there's something which I would call public-private keys, which is just a private key which is somewhere on the internet, basically. The Debian OpenSSL bug. In 2008, it was discovered that Debian had a patch in their OpenSSL package, which was basically for some debugging, and that broke the random number generation, and effectively it meant that only the process ID was feeding in the random number generator. The process ID is 15 bits, so that's not a lot. So basically you could just generate all the keys that this vulnerable OpenSSL version would generate, and then have a list and compare against it, and then you have a private key. So simple attack, generate all possible keys, and then compare to a list. What makes this a bit more tricky is that there are quite some variations, like you can generate keys with OpenSSL directly or with OpenSSH, which is also using OpenSSL, but then the state would be different, so the keys would be different. Also the keys, the output depends on the architecture, 32-bit versus 64 bits, and a few more things. So effectively it's a bit more than 15 bits, but the number of keys is very limited. So you can generate all the keys. So this was 14 years ago, so surely there wouldn't be any such keys in use anymore, right? In 2020, it was discovered that there was a TLS certificate issued by a real CA, like a web trusted certificate, with one of these Debian keys. And I actually checked, I found another certificate from 2021, which was a bit interesting because it was a key generated by OpenSSH, but used for TLS certificate. Yeah. So, and the problem here is that they're like, it's relatively trivial issue, but there are these variations, and so people have sometimes, they have like tested against lists of compromised keys, but these lists were incomplete, so they were missing things, and yeah. And I hope my tool will at least catch all the significant ones. The problem is also a bit like you can have RSA keys with basically any size, so you cannot iterate over all key sizes, but there are basically 3 common key sizes that people use in practice. So, yeah. Then the common prime factors vulnerability. In 2012, there were 2 research teams that basically independently discovered an issue with RSA keys with common prime factors. So we need to get a bit into how RSA keys look. I hope it's not too much math, but it should be relatively easy. So such an RSA public key is 2 numbers basically. They are called N and E, and the N number is the interesting number. This N it's called the modulus, and it's a product of 2 prime numbers. We call these P and Q. So N is P times Q. And these 2 primes, they need to be secret. Like, if you know these primes, then you can calculate the private key. So, and that's also why RSA depends on factoring being hard. Like, we have a large number, and splitting that into prime factors is a difficult problem. So we have no efficient way of doing that, and that is the basis why RSA is secure. Okay, now you could imagine, we have some keys where something was wrong. We have one key that is the product of prime 1 and another prime, and we have the second key that is the product of prime 1 and another prime. So we have one prime is different and one prime is the same between 2 keys. Why would that happen? Things go wrong. If you have such a key, such 2 keys, then you can do something which is the greatest common divisor, which there's an efficient algorithm for that. If you had math in school, you should have learned it. It's not that difficult, but this is fast. You can calculate this within milliseconds. So if you have 2 of such keys, you can generate this, and then you have one of these primes. And then you can calculate the other, and then you can calculate both private keys. Okay, so why would this happen? First of all, so this works for 2 keys, but there's also an algorithm which is a bit more sophisticated, but reasonably simple to implement, where you can do this for a large number of keys. And there's an implementation from one of these research teams that published that in C, which works very well for millions of keys. So what you can do is you take all the keys you find on the internet, I don't know, you do a scan on TLS or something like that, then you ran this algorithm, and then you will find broken keys. And you can still find these broken keys today, of course. So then you might wonder, why do such keys exist? I mean, it's broken, like, why would anyone generate them? And it is, in almost all cases, something which is called an early boot time entropy problem. So what you can imagine here is happening. You have a Linux system. It boots, and right after boot, we don't have that much randomness, particularly in something like an embedded device, where there's no keyboard, no network, whatever. And maybe this embedded device, on the first boot, it generates a cryptographic key. And then it generates a prime at a time where the random number generator is not properly initialized. So it generates kind of a bad prime, and then the next device generates the same prime after boot, and then some more time passes, the random number generator gets initialized, maybe its network is starting or something, and then the second prime is kind of a good prime, so you have a bad prime and a good prime, next device, bad prime, good prime, both of them share a prime and you can break the key. The Linux kernel developers implemented some countermeasures, and a lot more recently actually, but already right after this vulnerability was discovered, they implemented some things that should make sure that more entropy is added to the pool earlier, and this should not happen with any kernel published after 2012. But as you may know, in embedded devices, people tend to use like really old software. It's not unusual to have, apparently have 10-year-old kernels on devices. And there's actually a paper from students from one of the researchers who discovered this in 2016, and what they did is they analyzed this vulnerability over time, like they had TLS scans from various years, and it was kind of, you could not really see this going down. Like you found roughly the same number of keys in every year. And also they discovered that, okay, new devices were showing up with this vulnerability after it was discovered. And also a lot of the vendors that had been informed about this vulnerability apparently didn't ship any fixes. So this is a bit of a frustrating read if you want to, like, how disclosure and fixing stuff doesn't really work. Yeah. And now, in my tool, I want to check for this, but obviously I cannot on the fly compare a key with millions of other keys. But what I can do is I can run this attack on multiple data sets and then have these prime factors and have a list of them. Then I multiply that list and then I calculate a GCD between that list and the modulus that I want to test. And if that does not output 1, then I know the key is vulnerable. If you didn't get that, doesn't matter. I have a check for that, and like I have an efficient way to check this against known prime factors. But only against known ones. I cannot know if there are other devices that I don't have in the keys that I have access to, but this works reasonably well for all the kind of known affected devices. Yeah. Then there was a vulnerability return of the Coopersmith attack in 2017. I'm not going to go into the details of that because it's heavy math and I also don't understand it. But it's like Coopersmith's attack is kind of one of the classic attacks against RSA, and they found apparently that some chips from Infineon generated RSA keys with a pattern that they could use to attack them. The attack is expensive, like it takes some 100 CPU hours, but it's doable. This was like in things that were used in smart cards, in TPM chips, YubiKeys, things like that. So kind of embedded stuff. I already mentioned Estonia, they had to replace 750,000 ID cards due to that vulnerability. What is also interesting that these chips, they were actually certified both by FIPS and common criteria. We're in Germany here. Is anyone working for BSI? They certified that these chips are okay. The attack is expensive, but there's an efficient check. So if you have a key, you can easily tell whether it's affected by this vulnerability. The researchers published code, and I kind of just took that code, threw everything out that I didn't need, and used it in my tool. And then I already mentioned earlier, which was kind of the motivation for doing all of this. There was this bug in this keypair library, which was discovered last year. So it's a library in JavaScript which can generate RSA keys. And it happened that apparently this library sometimes produced the same keys. So you had duplicates. Unfortunately, the disclosure, they were very scarce in details. So they mentioned a bit how the vulnerability worked, but they said, we have informed our users who had such keys, but they didn't say anything about how they identified these keys. They didn't share anything which you could use yourself to identify such keys. Yeah. I contacted this company that's developing the Gitkraken software, and they refused to share any information about it, which I found unfortunate. So what's happening in there is that this library has there are two bugs. One is that they are checking whether they have a good JavaScript random number generator, but this check had a bug, so it always failed. And then they had a fallback random number generator they wrote on their own. And that did some byte string conversion things, which ended up that you could only have values from the strings 0 to the string 9, and the string 0 would be much more likely because it was basically for any value it would output 0 except for the values that match the ASCII ID of 1 to 9. Unfortunately, that still is enough variation that it's not feasible to generate all the keys. But if you generate a lot of these keys, you will notice some patterns. There are some keys that are much more likely than others. And like, I'm still kind of analyzing that. It looks to me a bit like there are kind of three buckets, like keys which are very common, keys which are somewhat more common, and keys which are not so common. Yeah, but but what I'm doing to check for that is basically I have a large list of hashes of keys and check against that. Yeah. Then the Fermat attack. There is a factoring algorithm from Pierre de Fermat, the famous mathematician, which was, he described it in a letter in 1643. And this algorithm works well if you have a product of two primes and the primes are close. What does that mean? It basically means the difference between these two numbers is not so big. So on the upper bits, they are all the same. On the lower bits, maybe they're a bit different. Maybe they differ by a few thousand or even a few million. That would be a close prime. And there, this factoring algorithm works really fast. Yeah, so remember, an RSA public key has this n value, and if we can factor that value into its primes, then we can break the private key. Yeah, that's I already said. So yeah, and I figured out that there's a library called SafeZone from Rambus. It is used in some printers from Canon and from Fujifilm, and this was vulnerable to this attack. Apparently what they did is they generated an RSA key by generating a random prime and then looking for the next prime after that, which then would be difference like a few thousand. Yeah. Yeah. Then we have what I would call public-private keys, which is basically if you use a private key and the private key can be found on the internet, then it is not very secure. Yeah. Why would you do that? I mean, there are various reasons for that. The one is there's firmware which contains a key, like you have maybe a router or something, and the firmware just has a static SSH key or static TLS key. There have been a few projects where people have tried to extract keys from firmware. One was like the House of Keys project by SecConsult a few years ago. There's a somewhat older project called Little Black Box. And yeah, and then there's things like example keys in software, like for example, OpenSSL, they implement cryptography. Obviously they have some tests in their software, and in the tests they have some private keys that are just part of their test suite. Or you have standards that have keys, like in an RFC document there's an example private key. And then there are other things like people accidentally upload their keys to GitHub, or there are keys in documentation, all kinds of stuff. There is a repository on GitHub which is very interesting. It's just collecting private keys that for some reason have become public. I sent a bunch of pull requests to this repository, so it covers more things. Yeah, and I'm generating a list of hashes from that repository, and comparing keys against that. Yeah. So, yeah, that's what I just said. Yeah. I want to mention a few implementation details, how I'm doing this. So, first of all, I'm doing kind of three kinds of checks. One is algorithmic checks, which is like the Fermat attack, where I'm just trying the attack, and if it works, I have broken the key. Or ROCA, where I have an algorithm to identify vulnerable keys. And then I have these hash block lists, where I just have hashes of keys that are broken. This is for these public private keys, but it's also for things like the Debian Böck or the keypair bug, where you can just iterate over all the keys generated by a vulnerable implementation. And then I have one thing which is kind of a mix of both, which is this common prime factor vulnerability, where I'm comparing against a list of known prime factors. For this block list, there's a few things to consider how you best implement that. I mean, okay, you have a list of hashes and then you do a binary search. That's the easy part. But what are you hashing? Like, what people usually would do is they would take the public key and generate a hash over that in some format that always encodes has a deterministic encoding. But I figured out it's better to just hash the modulus of an RSA key. And the reason for that is if you have two keys which are broken for whatever reason, and they have the same, like one of them is broken for whatever reason, and another key has the same modulus and a different exponent value, which is like the other value in an RSA key, then it's also broken. And the reason for that is that by knowing the private key, you can factor n, and from factoring n, you can calculate the other private key. And this matters. For example, this Debian OpenSSL bug. OpenSSL has a command line option to set the exponent value to two different values. The default is 65,537. This is recommended because you can calculate it fast and it avoids a few attacks. But older implementations have used 3, which is a bit more problematic. Anyway, we have two different values here that are possible. And if I would hash the whole key, I would have doubled my number of keys I have to check. And if I just hash the modulus, then I have covered all of them. Then most of the checks I have are about RSA, and there's really, it's not intentional. I mean, first of all, okay, RSA is the most widely used public key algorithm, even though it's going a bit out of fashion, but it's still the case. Like, most cryptographic keys are RSA. There are more implementations, so there are more bugs. But also, like, you might ask, yeah, but what about elliptic curve? What about DSA? There isn't really any vulnerability I know of in key generation that would fit into that kind of setting. There are vulnerabilities with elliptic curves that affect signatures, but then you would kind of have to test the signature, and it also doesn't work for like single signatures, but you have to test many of them, so that doesn't really fit in my framework here. So I have a list of broken keys, of keys like from like static keys, but I don't have any further checks here. Okay, now we could apply this tool to collections of keys. Because now we have a nice tool to check for all these vulnerabilities. What do we find if we apply it to, I don't know, TLS keys or SSH keys? Like, I did a scan on SSH host keys. I got like 16 million keys. And there were around 18,000 static keys from firmware. So that's apparently quite a common thing. So you have just devices that support SSH for whatever reason, and the key is just hard-coded in the firmware. Then there are a few Debian OpenSSL bug, more than with TLS, I found out. So people don't rotate their SSH keys so often because SSH key rotating is a bit more problematic. And then there are a couple of these common prime factor issues. Then I had a data set of TLS scan, but I should mention here that this data has a bit of a bias because this is a list of certificates and they removed the duplicates. So if I have like 1,000 routers with the same TLS certificate, it would only show up once in this data, which is the reason why you cannot directly compare this to the SSH scan. But also here we see again that we have the most common thing is that you have just static keys from firmware. The common prime factor vulnerability is still very common. Then there were a number of keys. This is Fermat attack. These were actually almost all printers from Fujifilm, which is where I discovered this issue, and then I contacted Fuji and then figured out this is this Rambus library. Yeah. Then certificate transparency. If you don't know, these days, if TLS certificates get issued, all of them get logged into something called certificate transparency, which is a system of publicly auditable logs for certificates. And there are a lot of certificates in there, actually. It's, if you take all of them, that is currently 6.5 billion. And I took like the ones since January last year, because that is basically the time frame in which the certificates may still matter, because the maximum lifetime for a certificate is about a year. So I'm not very interested in what happened 10 years ago, right? So, the numbers are much smaller. I mean, you see the number of certificates I tested here is much bigger than the previous data sets, but the numbers of findings are much smaller. But still, there are a number of certificates with common prime factors. They were all expired when I found it. I don't know what happened there. They all were like small web pages from Vietnam. I assume there was some web hosting company there that somehow used some broken RSA implementation. Yeah, then again I found a few keys vulnerable to this Fermat attack. They were mostly for Canon printers, because these Canon printers had a feature to generate certificate requests, and then you could supply that to a CA and get a real web trusted certificate for your printer. And then there were 20 keys vulnerable to ROCA, and this is also a bit of a mystery to me, because when this ROCA vulnerability was found, people of course looked, are the TLS certificates affected? And the answer was basically no, only things like S-MIME certificates and what else, but no TLS certificates. But apparently for some reason Yahoo at some point issued TLS certificates vulnerable to ROCA. Yeah. I reported it, they got revoked, yeah. What should be noted about this data is certificate transparency. These are publicly trusted certificates, so the kind of certificate that your web browser will accept with the green lock icon and stuff. And vulnerable keys in there are far less likely. And the reason for that is, like, usually certificate authorities should check keys for known broken keys, but the rules there are a bit fuzzy. Like, there was this issue with that one CA issued a certificate for a key vulnerable by this Debian bug, and there was a discussion after that, like how much are CAs required to do these checks. Hint, now they can use my tool and they will be covered. I'm not sure if anyone already does that. And also, if a TLS certificate publicly trusted with a broken key is found, then it needs to be revoked if it gets reported. And that happens within 24 hours, which is kind of, sometimes creates a bit of a disconnect with usual disclosure timelines. Like when I reported this thing to Yahoo, I said, yeah, like I reported it on their HackerOne program, and then I said, oh, by the way, I will also report it to your CA, and they will revoke it in a few hours, and then probably you will have some problems, but yeah. I also found in this certificate transparency dataset 2 certificates which used as an example key from OpenSSL. This was also a bit of a mystery to me, because it was the same key, and OpenSSL has like 1,000 example keys. And apparently 2 people independently used this specific example key. I don't know why. These seemed unrelated. Yeah. Then it's demo time. Yeah, so there is the webpage badkeys.info. It has a form. You can enter a key. It supports a number of formats. It supports public keys, also supports private keys, but you should not submit your private keys. I will not store them, but don't trust this. Yeah, you can fill it with this example data from down here, but also I will just have some things. So here we have an SSH public key. And we enter this here. And then it will tell you this key is broken. This is from a device firmware. And you can find the private key here. And if you click on that, you will find a link to GitHub and you will find the private key. Yeah. But now, if you want to use this, maybe you're doing a pen test for an organization and then they have maybe, 100 SSH hosts and you want to test them all, and maybe it's a bit annoying to paste this all into this web page. So there's also a tool. So yeah, here we have a certificate from a printer. And we can run Badkeys, and then it will tell us Fermat vulnerability found. Yeah. This is Fermat vulnerability. This is also a nice feature which is currently only available in the web interface. If you paste this, so this is a TLS certificate, but TLS certificates contain a public key. Okay. So we can paste this on the web page. And this will break the key on the fly. Like here you have the private key for this certificate. And then you may have something like you have a large number of keys. So here's a file with SSH keys, 1 per line. And for this I also have a mode which is called SSH-lines. Then you can pass that file and it will check all the keys in there. And you see there are some keys vulnerable by this Debian OpenSSL bug. And by the bug for the OpenSSH variation in x86 architecture. There's something similar for certificates. So you can have a file like this, which is base64 encoding of a certificate, and then you can have something like an ID behind it, because if you have a list, maybe you want to find afterwards which certificate was it. So in this case, they have an idea, and then you can do Badkeys -cp-, and then this is a bit of a larger list, so it will take a while, but yeah, then it found a few certificates which were vulnerable to ROCA. And also the last mode I have there, you can just have RSA moduli in hex values. There's a parameter m, and then it will just scan that for the vulnerabilities. Yeah, and this is from some live TLS scan, so there's a number of different vulnerabilities in there. Yeah. Yeah. Also, I want to show you, like, this is an RFC document, like these internet standards, and it has a private key. And maybe sometimes people use keys from standards because, I don't know, they don't know what a private key is or something. You can add that, and it will tell us, yes, this key is broken. It's part of an IETF RFC. And also linked to the private key. And this is an elliptic curve key, so for this blocking of known keys, this is also supported. Yeah. Okay, so what's this good for? Yeah, obviously, if you do a pen test or an audit, you have a company, they have SSH hosts, you have no idea where these keys were generated. Maybe you want to test them for known vulnerabilities. Same with web interfaces for TLS. Publicly trusted certificates, you will probably not find much, but for things like internal device interfaces, they may be vulnerable to things like that, or whatever people use their public keys for. You can test them with this. Then, but also if you're in a position where you have users and they provide public keys to you, then it's a good idea to check them for known vulnerabilities, because if your user submits you a key and this can be broken, then you want to warn them about it. And a typical situation would be something like a code hosting platform like GitHub. Their users submit their SSH keys, and of course it's a good idea if this key is broken, tell your user. But also certificate authorities, I mentioned this earlier, they are kind of obliged to check keys, so it makes a lot of sense. If someone wants a TLS certificate and supplies a key, then check if that's affected by any known vulnerability. Yeah. The code is open source. It's published. It's written in Python, published in an MIT license. So yeah, please use it and use the webpage. And yeah, thanks for listening. We have a question. Yeah. Are there any questions?
For the elliptic curve checking, you could check broken keys if the coordinates are belonging to the elliptic curve, because one of the attack would be to send coordinates which are not.
So this would be an invalid turf attack.
Yeah.
The issue with that is that if you try to import such a key, by almost all standard software, it will already be rejected.
Okay.
So, like I'm using Python cryptography, and if you have such a key and try to import it in Python cryptography, it will already throw an exception and not even pass it.
But
which is also why I think that you will not find this in the wild.
Okay, so you don't expect that would be on an embedded device or other crappy...
No, because it wouldn't work.
Okay.
Like, most implementations will just fail if you try to use such a key. So there has been an attack with this a few years ago, but this was for elliptic curve Diffie-Hellman with static Diffie-Hellman keys. But yeah, that's kind of a different scenario. But I'm aware of that attack, but it doesn't really fit here. Okay.
Is there an API that you can use it for other scanners?
You mean like an online API or?
An online API, yeah.
No, I have thought about that, but then I thought, like, if you want to use it, then just download it.
Yeah. Okay.
I mean, if there's a need, like if you feel that this would be very useful, then you may write me an email and we can talk about it. It wouldn't be difficult, but I felt it's not that necessary.
Okay.
Don't be lazy. Send a PR.
Yeah, I mean, what's the difference whether you send it against an HTTP host or whether you send it against a command line tool or use a Python library? And then you have it under your own control, and that's better anyway. So.
No more questions, then thank you.
Oh.